Okay, how did you make out with number 7? In number 7, you're given a graph, and the graph kind of indicates where the x-intercepts are, and you're asked to just give information about this function without ever knowing the equation of the function. Well, we can look here and see that the graph crosses the x-axis at -1, and then at +1, and then again at +5. So our x-intercepts are -1, +1, +5. Then we're asked, what is the lead coefficient here? What is the coefficient a that is multiplying the x cubed term? Well, in this case, we're asked, is it negative or positive? In this case, we're coming in from above and we're leaving going down to negative y values off to infinity there, negative infinity. So therefore, the lead coefficient a must be a negative number. And finally, we're asked what type of equation is it, and I kind of tipped my hand. The highest order term is x cubed, so it's a cubic equation and a cubic function. Now, number 23. They give you this function, they say graph that. Well, luckily, of course, they make it so that it factors real nicely. I set the function equal to 0 so I can get my x-intercepts. I factor completely, and I see that x is 0, x is 5, or x is -5. So I can go on the x-axis and indicate my 3 x-intercepts there. And let me fix my smudge here. And now I can look at my lead coefficient and decide if it should go this way or this way. The lead coefficient is right here. It's the -1 multiplying the x cubed. So, since a is a negative number, I start off at positive infinity. I will finish going off to negative infinity. And that's what my curve looks like. If you want more detail, pick some values in between, like 2 or 3, and you'll be able to locate more points on these humps. And by the way, keep in mind that the minima or maxima, that is the extreme points, do not have to occur right in the middle between x coordinates. They can be slanted over towards one side or the other. In the middle between x-intercepts, I should say. They can be closer to one than the other. So you don't have that kind of symmetry that you had in a parabola. All right, so you've all mastered cubic functions. Let's talk about quartic functions now. These are 4th degree polynomial functions. So we just add that term on. And of course, specify that a is 0, or else that term wouldn't be there. Now, the simplest case of all is f of x equals x to the 4th. This is figure 6.6 on page 432. This is part A. Simplest of all. How many terms? 1. So you might think like, well, wait a minute, now, the degree is 4. Aren't we supposed to have 1 term less than the degree of the polynomial? And I said, yeah, but sometimes terms are missing. And when they go missing, they miss in pairs. You won't just lose 1, you'll lose 2. So, look at this to see what I mean. In this case, we had the ultimately simplest quartic function. There was an x4th term. There's no other terms. Look at this one. Just the same, but with one other term introduced. We have x to the 4th minus 3x squared. This is part B of the same figure. And you see what happens when I introduce this x squared term, it causes things to start wiggling around. In this case, I see there are 3 x-intercepts, and there are 3 turns, right? I'm driving down here, making a left turn, making a left turn, making a left turn, left turn, left turn, till I get right there. Momentarily, the steering wheel is straight for an instant. Then I start making I'm coming down here, I'm making a left turn, left turn, left turn, left turn. Come down here, steering wheel is straight just for a split second. Then I go to start making a right turn. I'm making a right turn all through here, through here, through here. Steering wheel is straight, start making a left turn again. Away I go to positive infinity. So I see the 3 turns that I expect in a full-blown quartic equation. The high order coefficient is +1, so the curve goes upward. Comes in from upward, goes away to upward. And in this case, I happen to see 3 x-intercepts. But that's because this hump here lands right at the origin. If I were to subtract 1 from that function, everything would shift down 1. We know that from our work graphing this semester. That pushes a curve down, in which case we'd only have 2 x-intercepts. Suppose I added 1, it pushes the curve up 1, in which case I'm going to hit the x-axis twice on this middle hump. So you see how these changes can play out. Different possibilities are possible. Okay, if you want to see it algebraically, let's just set the function equal to 0, right? We'll set y equal to 0. I see that I can factor out an x squared. Okay, so my solutions are going to occur where the first factor equals 0, x squared equals 0, which means that x is equal to 0, or where x squared minus 3 equals 0. If I solve that using the square root method, x squared equals 3, I take the square root of each side, I get x equals plus or minus the square root of 3. And those are the numbers here. That's where x is 0. This is where x is positive square root of 3. This is where x is negative square root of 3. All right, let's do a more complicated one. Here's an example I found from your homework problems. It's actually number 27. There wasn't a good example of this in the text, so that's why I'm using a problem out of the homework section. Graph this function. Y equals x to the 4th minus 4x squared minus 12. This is going to incorporate a few of our skills. Notice that this is a quadratic type. This is an expression of quadratic form. I can substitute. I can say let u be the same as x squared. Then, substituting, I get that. And just as we saw when we learned this a week or so ago, this is a very easy quadratic expression to factor. I set it equal to 0 to get my intercepts. Okay, that's supposed to be an equal sign. Set each factor equal to 0 to solve. On this side I get u equals 6, on this side I get u equals minus 2. but I want to know what's x. So I substitute back. U is just the same as x squared, so x squared equals 6, so therefore x equals plus or minus the square root of 6. Over here, x squared equals negative 2. You can't have a real number which when squared gives you negative 2. You only get a complex number. So we say there are no real roots on this branch of the solution. We'll see what that means graphically. Let's go ahead and plot this thing. Plus or minus square root of 6. Well, square root of 6 is a number that's between 2 and 3. So one x-intercept is there. The other one is there. The lead coefficient is the invisible 1, so it's positive. So this thing's going to come down, have the hump, and then go up, right? But the middle hump has to be below the x-axis because we have no more x-intercepts. So in other words, we're going to come down like this, going to have a hump, and go back up. Now, we can also look at this and say, oh yeah, the y-intercept is negative 12. So this number over here must be negative 12. All right, so we have good information about our graph. And that's a pretty accurate graph. Of course, if you did it on a calculator or using a graphing program on the internet, you could make it really accurate, but this certainly gives us a good overall feeling. Now, the fact that the hump is entirely below the x-axis means that there's no more x-intercepts. If the hump was up higher and crossed the x-axis a couple times, we would have had roots. This would have worked out so that we got some real roots here. The fact that we did not get real roots here is the same as the fact that the hump lies entirely below the x-axis. We could shift the curve up, right? Suppose we added 12. In fact, then we get minus 12 plus 12, they would cancel out. We'd solve this thing, it would land right there, so we'd have 3 roots. If we added 100, it would be well, maybe it'd be too high. That might lift the whole curve above there and be no x-intercepts. But if we added like 15, then the curve would hit the x-axis in 4 places, I'm pretty sure. Okay. Now, I want you to do another one of these, number 25, in the homework. So pause the video here and work out number 25, but let me give you a hint. Your quadratic expression, in this case, has x's in every term. That means you can factor powers of x out. See what I mean? So the original quadratic expression can be written like this, and now, in fact, this will even factor. So you can figure out your x-intercepts pretty easily like that. So give it a shot, and we'll see how it works out. Okay, how did you do? let's set our function equal to 0. This quadratic expression factors like this. So I'm going to get x equals 0 and x minus 2 equals 0, which gives me x equals 2. So there are my x-intercepts. Meanwhile, I expect to have 3 humps, right? Zero, 1, 2. So I have x-intercepts there and there. The lead coefficient is a positive 1. So the wings come in like this. And the remaining question is the hump over here above the x-axis, or is the hump going to be below the x-axis? I know we're not going to cross the x-axis in the middle here. We've run out of x-intercepts. So what I would do, I'd plug 1 into the function and see what I get. F of 1 is going to give me 1 to the 4th minus 4 times 1 cubed plus 4 times 1 squared, which equals 1 minus 4 plus 4. 4's cancel out, and I get 1. So the point 1, 1 is on my graph, and now it's clear how the graph must go. This must go up into the middle hump here and then back down. Like that, we have our hump above the x-axis. For homework in this section, on page 435, 1 through 19 odd, and then number 28. Okay, but not to be outdone, we are also going to take a quick look at modeling with cubic and quartic functions. This is section 6.2. So maybe we'll take a little break right here and then we'll come back and do section 6.2 very quickly.